Okay, so this is probably one of the most challenging subjects that we kind of talk about in chemistry, and because it's extremely abstract and it's in a way it's kind of hard to relate to. So I'm just going to go ahead and preface this with this. There's nothing easy about stoichiometry now, because of what I'm asking you to do. But let's go ahead and just kind of run through some things and kind of put this in perspective. Chapter 3, of course, is about, that's what I'm calling this, is chapter 3, is stoichiometry, and this is the measurement of matter. And you guys remember that that matter is anything that has mass and, of course, takes up space, and we call that volume. So anything with mass and volume. So we talked about energy in terms of electrons the first quarter of the semester. So this one we're going to devote to talking about mass and things that take up space. Okay, so some of the concepts that we'll cover, the concept and the use of the mole unit. Mole is going to be Latin for pile or mound. And that's exactly what it means. It's just a pile or mound of any substance, and it doesn't matter if it's calcium carbonate or iron 3 oxide. We can look at the mole for that. So it's used for counting. We've got to have a way to count these exceptionally small creatures that we deal with. So atomic and molecular weights, so the masses of atoms. Let me try to roll this up here. The masses of atoms, or the elements and the molecules and compounds. We're going to look at percent composition, and that's going to be your bubblegum lab. That's why I had you guys bringing in bubblegum today. And then empirical formula analysis. We're really getting down to the nitty-gritties of the ratios. And if you remember using those charges and balancing charges when we talked about nomenclature, this is going to come into play. And then, of course, then it gets us into the uses of the balanced chemical equation, looking at product yield, limiting reagent, and percent yield. But let's start with the very basics first. And you have your notes in front of you. So as we're kind of working through this, I want you to fill it in and just kind of jot down things. And if you have questions, write them in the margins of the paper that I've provided. All right, it says, how many atoms can you see with the naked eye? And the answer to that is 1 times 10 to the 15th. I need that number of atoms. Okay, so let's put that in perspective. 10 to the 9th would be a billion. And if you get much beyond that, I'm pretty much useless as far as these numbers because they're so astronomical. The bottom line, it's a lot. And since atoms are so small, we got to have a way to count them. We got to have a way to measure them as we're working in the lab. Now, this is not new. We do this all the time. So, for example, you got a dozen eggs, you got a case of Pepsi, you got a gross of pencils, and then you got a mole of atoms. So let's kind of fill this in. So what, 1 dozen eggs, we say is 12. A case of Pepsi, we're just going to pretend like that's 24. A gross of pencils, this is going to blow your mind, it's 144. And 1 mole of atoms. 1 mole of atoms is going to be this. Okay? It's going to be that number. And this is called Avogadro's number. And it was named after this Italian chemistry aficionado. His name was Amedeo Avogadro in the mid-1800s. And then everybody always asks the question, why do we use this number, the 6.02 times 10 to the 23rd? And it says, well, if you were to measure out 12 grams of carbon-12, now remember, this carbon-12 is based on the most abundant isotope. Excuse me. The most abundant isotope. Because if you remember from the Candium lab, when we talked about percent abundance and relative abundance, so carbon-12 is going to be the most abundant. It's going to contain this many atoms of carbon. Okay? So there is a relationship between the mass and the number of moles of a substance. Okay, so let's take a look at this chart. Now, I've already got some stuff penciled in. I'm going to go ahead and clear the annotation so we can kind of work through this together so that you're not confused. So we're going to start with each one of these. These are elements, of course. And then we see a compound that you are very familiar with. And we're going to record their weights. And these weights, or the masses, are coming from the periodic table. The mass of lead is going to be 207 grams per mole. And I know that you don't really know what this unit is. I just want you to get into the habit of writing it because you're going to need it. Let's go ahead and do fluorine. And I think she's about 19 and maybe some change, or maybe she's 18 and some change. But let's go ahead and round this up just to make these numbers even and something very easy to work with. And of course, hydrogen is 1 gram per mole. And of course, water, if we look at water, and it's going to have 2 hydrogens, so that's 2 times 1.008. I know I just lied and said we're going to round up, but and then there's 1 oxygen, and that is going to be 15.998. And when you add these together, you're going to get somewhere in the neighborhood of 18 grams per mole. Okay, so all I'm doing is adding up the elements, and of course their number and their masses based off the periodic table. Okay, so the question said, well, how many atoms? Now, if I go back to my previous chart, it said that if you were to measure out 12 grams of carbon-12, it's going to have this many atoms. So I should be able to apply the same logic here, and then say for 207 grams, I'm going to have 6.02 times 10 to the 23rd atoms of lead in 207 grams. Same thing goes for fluorine. You're going to have 6.02 times 10 to the 23rd atoms. And then for hydrogen, you're going to have 6.02 times 10 to the 23rd atoms. And of course, the last one is going to be the same thing, Munchkins. Even though we're talking about a compound, compounds are going to be made up of elements. And elements have mass. So we got the same story being told over and over. Excuse me, it's not mass. Well, yeah, I guess it would be. So it'd be atoms of hydrogen, atoms of oxygen. So right here, the conclusion, it says 1 mole of water contains 3 moles of atoms. Now remember, mole just means a pile or a mound. I always think of flour. Excuse me, I always think of flour like cooking. Like I need 3 cups, or I need 3 tablespoons or 3 teaspoons. Like I think of it as a measurement that would create a pile or a mound. So 1 molecule of water contains 2 atoms of hydrogen and 1 atom of oxygen. And each of those atoms is this. That's pretty amazing. Now you're like, wait a minute. But they have different masses. That's true, Munchkins. It does. They do, each one. But they also have different sizes. And you learned that back, I don't know, how many weeks ago? You know, lead is a lot bigger than fluorine. And fluorine is a lot bigger than hydrogen. So that maybe that will help with the discrepancy in those numbers. Okay, let's just keep going. Okay, the atomic masses or atomic weights are summed together to get the molecular weight, and that's what I was kind of explaining a while ago with water. Let me roll this up again. So we have about 18 grams per mole, and so for every 1 mole of water, she has 18 grams, and 1 mole is equal to 6.02 times 10 to the 23rd molecules. Okay, so I'm going to be throwing lots of units at you, so just keep in mind. In order to keep count of the amount of matter that we are using in a reaction, we're going to have to be able to convert between moles and grams and molar masses and the number of molecules or the number of atoms. And so do you remember way back when I had you guys doing that dimensional analysis and I said, guys, if you'll just do it this way, I promise your life will be easier. Okay, so now we're going to finally come to this. So the first thing that I want you to do in practicing is I want you to calculate how many grams is in 1 mole of disodium chromate. And so here is the formula. And then we're going to calculate how many grams does 1 molecule weigh. So I want you to try to calculate the molar mass, if you will. All right, so let's write down that. Let's write down molar mass of disodium chromate. So go ahead and pause the lecture and try it, see what you can do with it, and then after that we'll come back together. Okay. Okay, so now you've taken the time to pause the lecture to kind of look at the disodium chromate, and let's do this one together. Let's kind of look at this, and you check your stuff out and see how you did compared with me. And as always, double check my math just to make sure I'm on point. Okay, so I've got sodium, and there are 2 of them, and each one weighs 22.989, I think 707 grams. All right, and then we have chromium, and there are 1 of them, and each one of them is 51.996. And then I have oxygen, and there are 4, and each one weighs 15.998 grams. And so, of course, you're going to multiply, and you're going to add these together, and you should get somewhere in the neighborhood of 161.934 grams per mole. Okay? Now, at this point, we're going to phase into the second part of the lecture, but you're going to do an activity first. So each of you should have gotten a copy of the Moles of Chalk Lab. And you are going to, using the triple beam balances that are sitting on the round table, you guys are going to, you're going to have to take turns doing this, but you're going to get a piece of chalk, you're going to weigh your chalk, and then you're going to go outside, and on the steps right outside Mr. Adams' office, you guys are going to write your name. You're going to write your name using that chalk, and then you're going to come back and you're going to measure it and, of course, record your data, and you're going to work through the calculations. And it's going to work with atomic mass, and it's even going to talk about the number of atoms. So I want you to do that now, and then we'll have part 2 of the lecture.